All right, here we go. So we're looking at inverse matrices today. So we're going to start off with a quick definition. So our objective is to find and use inverse matrices. We're mostly going to learn how to find it today. We'll learn how to use it more tomorrow. So the inverse of a 2 by 2 matrix, which they're calling capital A, they just put A, B, C, D in here to give us a formula. If you do A inverse, this is the notation for the inverse of matrix A. It does not mean a power, you do not flip it over. It's the inverse of matrix A, and this is how you get it. It's 1 over the determinant of the matrix. So you would have to figure out the determinant, which we learned in the last lesson. And then you do some strange things. So A is here and D is here. You switch them and make this D and that A. So basically these two numbers switch places. You do not switch signs. And then on B and C, they stay in the same place, but you switch the signs. Somebody a long time ago figured out that this works, and so that's what we use. You'll see. Just wait.
I second Miranda's question.
No. So it works basically.
That's a weird name.
It's created to solve systems of matrices. So we're going to get into some systems tomorrow and learn a new way to solve them and some story problems that go with systems. And so what they did was they rearranged things like you would with the elimination method that you guys did the last, 3 years, and just put it all in here so that you don't have to think about it.
Is there a plus or minus in that one over the?
Nope, it's just whenever. So these just change signs, those switch places. Here is the determinant. And the determinant right here, remember that, so for this, because it's in the bottom of a fraction, it can't be 0. If you get 0 for the determinant, then that means it does not have an inverse. So not every matrix has an inverse. So you will see that crop up on assignments. You might have one where it just doesn't exist. So after you do the determinant, you're pretty much done. And we will look at that in a little bit. Okay, so we're going to do an example. So here is matrix A. So the first thing that we're going to do is calculate the determinant. So the determinant, you basically do some multiplying across. You're going to take 2 times 5, which is 10, and then you subtract 3 times 4, which is 12. And we end up with -2. So to find the inverse matrix, which is matrix with the little -1, it's not a power, but they're using that to represent inverse, you'll have 1 over -2, or in other words, -1/2. And then we take our matrix and we're going to move around the numbers. So 2 and 5 switch places. It becomes 5 and 2. And then the 4 and 3 stay in place, but we're going to change the signs to make those negative.
That's right.
And then your last step is to distribute this -1/2 to everything inside, so you're just left with a matrix. So it's -1/2 of 5, which is -2.5 or -2.5. -1/2 of -4 is 2. -1/2 of -3 is 1.5.
-1.
And then that would be -1. So
You're
basically, you just distribute that out. That is scalar multiplication that we did on the first day of matrices. And then this is my final answer right here. So if you want to, I'm actually, instead of boxing it, I'm going to box it with a highlighter just because when you box square brackets, it looks
unusual to me.
funny. Okay, so that's my final answer. We're only going to learn how to do the determinants by hand with 2 by 2 matrices. It's a little bit more complicated with 3 by 3s and bigger things, and I will show you guys some tricks later for those. Okay, so coming down to the next one, here's matrix A. So the first thing you want to do is find your determinant. So we take -3 times 1, which is -3, and then subtract -8 times 2, which is -16. We have a double negative there, cancels and makes it positive, so it's actually -3 plus 16, which would be 13.
Oh.
So when we go to do the inverse of A, we're going to have 1/13, and then we'll switch things around inside the matrix. So What do we need to do with the matrix now?
You gotta flip A and D.
Okay, so flip A and D, so that's a -3 and 1. So 1's going to go here, -3 is going to go there.
And just change the sign.
And then just change the sign. So this will be -2, and then -8 makes it +8. And then because this is a fraction that's kind of weird, we're going to leave this in fraction form. So if I take 1/13 times 1, it's just 1/13. If I take -2 times 1/13, it just becomes -2/13. So you can imagine this just being over 1. 8 times 1/13 is just 8/13. And then -3 times 1/13 is just -3/13.
Oh.
And I would just leave it just like that in fraction form. That's a weird decimal anyway. And if you leave it in fraction form like that, for some of the other stuff that we will do, it will serve you well.
Doesn't 8 need to be?
Miranda?
Doesn't 8 need to be negative?
No, because it was negative.
Oh.
And if we make it negative, it changes to positive. So good question. So the minus signs that we had in the formula up here basically mean change the sign. So if it's already negative,
Yeah.
it becomes double negative, changes to positive. It's okay. It's all right.
Still more.
Yes.
How long do you think it'd take you to figure it out if I did all of my work using like hexadecimal or something?
I wouldn't try to figure it out. All right. So it says find the inverse of A and then multiply A by A inverse. So this is going to take a couple of steps. So let's first, I'm going to start up here and try to save some room. We're going to find the determinant of A. So the determinant, if I take 1 times 6, that's 6. Subtract 2 times 4, which is 8, so we're going to get -2. So if I do A inverse, I'm going to have 1 over -2. We'll switch the 1 and the 6, so it becomes 6 and 1, those two numbers there. And the 4 and 2 are positive. We will make those negative, but keep them in their original places. And then just distribute everything out. So -1/2 of 6 would be... Good. -1/2 of -4
2
is 2. -1/2 of -2.
1.
It's 1. -1/2 times 1.
-0.5.
It's -1/2. I'm just going to leave it as a fraction. You could do -0.5, same thing. So that was the first step. So that's the first answer. So that's A inverse. So I should box that somehow. I'm going to use my highlighter so it stands out. And then they want us to multiply these together just to show you what the inverse actually does. So we're going to take the original matrix 1, 4, 2, 6 and multiply it by -3, 2, 1, -1/2. So we get to practice our multiplying skills.
Comes up to 3.
So we'll take 1 times -3 is -3 plus 4 times 1 is 4. So that'll be my first entry. So down here I will get a 1. Then if I take 1 times 2, that's 2. 4 times -1/2 would be plus -2 or just -2. So we get 0. 2 times -3 is -6. 6 times 1 is 6. We get -6 plus 6. So that's 0. And 2 times 2 is 4. And then 6 times -1/2 would be -3 or plus -3. I just did 4 minus 3. And you get 1. So this is a special matrix that we haven't talked about before. This is called an identity matrix. And this is what you get when you take a matrix times its inverse. Matrices do not have division. We did matrix multiplication, but we don't really have division. So if you need to do something that you would normally think of as dividing, we actually use inverse matrices. And so this is basically kind of like taking a number times its reciprocal and getting 1. This is called an identity matrix. And I'm going to give you some other examples of identity matrices in the next box. But this is what you should get if they are inverses. If they're not inverses and one of these numbers is off or more than 1, then something didn't work right. So it's a way that you can check your answers.
So that should have been in the checking your answers box?
Well, not sort of. We're going to add a little bit more.
Oh,
so if you're taking a matrix times its inverse and it's 2 by 2, you'll get 1, 0, 0, 1.
Does anybody like check their answers though?
Okay, so you're going to be required to a little bit on the assignment.
Nah.
So
That is
just bear with me.
answer it.
Okay, if it is a 3 by 3, it would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's a 3 by 3. I'll do a 4 by 4 and then we'll stop. You'll have the idea. So it would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So do you see the pattern on the identity matrices?
Yeah.
So basically you'll have ones from the upper left to the lower right, and then everything else comes out zeros. And something else that I will show you that is true with identity matrices, just so you'll know for what we're going to do in the next couple of lessons, where you have that little blank space over here. I know you're excited to fill that up. If I take an identity matrix and multiply it by another matrix, something special happens. So let's try that. All right, so Riley, give me a 2 by 2 matrix. Pick some numbers.
18, 37, negative 8, 12.
Good. I don't know how you did that so fast. All right, so we're going to take that times an identity matrix.
Why'd you pick such big numbers?
Okay. So we're just doing this to the side. It's in that little blank space.
Yeah.
So we just took a random matrix that Riley made up times the identity matrix to see what happens. So if I take 18 times 1, I get 18. 37 times 0 is 0, so I don't really need to add that on, do I? Because it was 0. And then on the next one, I'm going to have 18 times 0, so that doesn't get me much. And then 37 times 1 is 37. Negative 8 times 1 is negative 8. 12 times 0 is 0. We get negative 8. Negative 8 times 0 is 0. 12 times 1 is 12. We get this. So if you multiply by an identity matrix, so this is an identity matrix. If you multiply by an identity matrix, it's kind of the equivalent of multiplying by 1 with regular numbers. Like if I take 8 times 1, I get 8. That's what the identity matrix does for these. And that will come up at some point as like a step on something, and you'll just want to make sure that we have the identity matrix.